Good morning, everybody, or good evening, or I don't know which time zones are here. It's really a pleasure to present to you this presentation about preconception screening. We are going to focus in this presentation on actually understanding what preconception is, and then we are going to dive into understanding of what is residual risk and reproductive risks. We are going to make it by also using some live examples, and I would be more than happy to receive questions to answer during the presentation or at the end of it. Actually, we are going to have 15 minutes for questions at the end, or if following this conversation, any of you wants to contact me and ask questions, I will be more than happy to answer them. Let's just start with the disclaimer, some formalities, so we're just going to read it. So I just want to clarify that I am not a Thermo Fisher employee, and therefore I'm reading that Thermo Fisher Scientific and its affiliates are not endorsing, recommending, or promoting any use or application of Thermo Fisher Scientific products presented by third parties during this seminar. Information and materials presented or provided by third parties are provided as is and without warranty of any kind, including regarding intellectual property rights and developed and reported results. Parties presenting images, text, and material represent they have the right to do so. So that is the disclaimer, and with this, we can go to discuss preconception. So there's been a lot of progress in the last 2 decades in the field of preconception prenatal testing that we can allow to patients. So as you all know, we have started to use in a very robust and in much higher volumes chromosomal microarray which started already roughly 2 decades, and today many societies are declaring that chromosomal microarray analysis is the first tier test for different medical conditions. We are not going to deal with it during this presentation. And then you are all familiar, of course, with NIPT. So that is our ability to check if a pregnant woman is carrying an embryo with usually one of the three trisomies, 18, 21, and 13, and actually in 10 weeks pregnancy, which of course is a great advance. And now we are speaking more and more about the new revolution, which is actually expanded carrier screening. And what is expanded carrier screening? So as you all know, we are going towards a situation in which larger and larger parts of our genome will be made available to populations, which means that we do anticipate that our genome is going to be part of the medical records of each individual worldwide. That means, of course, that we can use more and more parts of the genomes to try and prevent the live births of kids suffering from monogenic autosomal recessive disorders. And if we're going to look at it and try to see what is the magnitude of this phenomena as a sec, then we all know that trisomy 21, of course, in the young ages is roughly 1 to 850 live births. And I believe that many will recommend and will agree that this is a syndrome that is worth screening for. If we're going to take a look at all monogenic disorders, then we do have something like 6,000 homing phenotypes. So if you are going to look to the online Mendelian inheritance website, you will find roughly 6,000 phenotypes that together are actually having an incidence which is almost 3 times higher than trisomy 21, and it is actually 1 in 300 births. So if we do think that we need to screen for this one, then it makes a lot of sense to include preconception screening for every couple planning pregnancy. If we're going to look at even one more number, so let's take it only severe phenotypes, so phenotypes which has either multisystemic damage or mental incognition syndromes like Tay-Sachs, like cystic fibrosis, that we are still going to be in roughly 1 to 600 live births, which is still higher than trisomy 21. So that gave a lot of motivation to try and offer a preconception screening which is as large as possible, and we're going to see examples very shortly. If we do want to take a very brief overview of what is autosomal recessive inheritance, then we have the mother, we have the father. Each of them is having one allele from their respective mothers and their respective father. Same here. And in this particular case, you can see that the mother is healthy carrier of an allele which is called B, and a mutation, specific mutation is this allele, and the father is also carrier. So this couple are completely healthy individuals, but they are carrying each the same mutation in a given gene. And then you can see that actually 25% of their kids will inherit the A and A, the two normal copies, and their phenotype would be healthy, and they will be not carriers. 50% of their kids will actually present the same healthy phenotype, but since they will inherit one defected allele with this specific mutation, then they are going to be healthy carriers. And 25% are actually getting both defected alleles, one from the healthy mother, one from the healthy father, and they will be sick in a homozygote state because they will have the same mutation affecting both copies of the gene. There's, of course, another way for autosomal recessive to be presented, which is compound heterozygosity, which in this time, the green color represents a different mutation in the same gene. So once again, the mother is healthy. She has one normal copy, one defective copy with a red mutation, and the father has one normal copy and one defected copy with the green mutation. The end results will be the same: 25% healthy phenotype non-carriers, 50% healthy carriers, and 25% sick, but in a compounded heterozygosity state because both uh, the two copies of the genes are defected, but each of them because of a different mutation. In preconception screening, we are also including many times X-linked disorders, like the screening for Fragile X, like the screening for Duchenne muscular dystrophy, and others. And in this situation, naturally, we must remember that a mother can be a carrier, so she would have one normal X and one defected X. The father has only one X, and this is why fathers are either sick or healthy, but because many of the X-linked disorders are not allowing to make it to reproductive health and reproductive age and so on, then almost always the fathers, of course, will be healthy and their X will be normal. And in this case, what that we can see is we can see that there is actually a chance of 50% from the males to be sick. That means that females will receive one X from the mother, one X from the father, and will be healthy. A male, if you will receive X and Y from the father, of course, will be healthy as well. And then it is enough that the mother will transmit her X to a male offspring that the kid will be sick. So that means here is independent of the father's genotype. It is dependent of the inheritance of the mother, and this is why it is a risk state as well. We do not screen usually for autosomal dominant disorders, so this is why I'm not going to detail it. But naturally, the inheritance of autosomal dominant is are clear and should we can get familiar with them elsewhere. Now let's define a little bit what is prenatal screening. So prenatal screening is one of the pillars of prevention medicine, of genomic medicine, of precision medicine. We want to prevent diseases. And prenatal screening is the systematic search for a specific condition among a large asymptomatic subpopulation selected by demographic characteristics such as age, sex, or ethnicity. Screening typically identifies at-risk groups for further diagnostic testings. So that is very important because many people are saying Yes, we don't need to be screened because we are healthy. These are exactly the individuals that needs to be screened because carriers are asymptomatic. And this is why preconception screening is suggested to all the population in campaigns of screening rather than to people who are sick, because those who are sick, we already know that they are sick. So that is very, very important to realize this. And screening is different from diagnosis. Diagnosis refers to any of the diagnostic procedures used to determine whether a fetus has a genetic abnormality. So that means if we screen the parents and we find that they are both carriers, we do not know if the embryo will be sick. We only know a diagnostic procedure will only be if, for example, by amniocentesis, we are going to take genomic material from the embryo and know exactly what the embryo carries. So this is very important. And one more important uh, definition is what is prenatal. So prenatal is actually everything before the delivery of the kid. And there might be population in which preconception screening is doing premarital, before marrying, some preconception, before the woman is pregnant. Prenatal is during pregnancy. So some might do preconception screening still within the pregnancy, let's say at the beginning of the pregnancy. Naturally, these couples will lose some treatment modalities such as IVF and PGD that can be offered to people who did preconception screening before the pregnancy. And then we have two more terms, which we should not be confused with them. One is perinatal, which means immediately after birth. And you know that there are genetic screening, there are screening, either biochemical or genetics, which are being done, for example, for hypothyroidism and for phenylketonuria. So that is perinatal. And then there is also postnatal, which is, let's say, a few months age or a year later on. So these terms has to be distinguished. And again, we are trying, of course, each couple has the right to choose what they prefer to do, but we are trying to get to the preconception state with the screening because that means that we will be able to interfere and intervene with the pregnancy before the woman is pregnant, because you know that pregnancy is, of course, something that is the clock is ticking and we can't stop them. So, what are the reasons now for autosomal recessive disorders in different human populations? So there are many cases in which there is founder effects, which means that a small group of people have give population, and by chance, by drift, many recessive alleles are in the population. One can note the Finnish heritage disorders, the Amish population, Ashkenazi Jewish population, and so on. Another reason for autosomal recessive disorders, and an example of the Middle East is being given here because consanguinity is practiced often, which means that two first-degree cousins might give a birth to a kid that has a defected identical copy from the father and from the mother because of an identity by descent state. So that's another, of course, reason. And as you can see in the pedigree, usually consanguinity is being shown by two lines. Then there are also genes in which there is pan-ethnic damage to the genes, which is try to imagine that this is like a bad road with repeated accidents in it because there's a bad crossroad or whatever you want to say. And those are the hemoglobinopathies, so thalassemia alpha and beta, cystic fibrosis, spinal muscular atrophy, Duchenne muscular dystrophy, and Fragile X. Actually, in one case, the hemoglobinopathies, as you know, carriers sometimes have some protection from diseases like malaria. So this is usually the reasons for having autosomal recessive disorders and the rationale behind suggesting it to the population. And as you can see, in the past, if we are going to take a look to the policy statements, then we speak about cystic fibrosis, a given disease, or European Jewish descent, which means that the focus was on specific genes and specific populations. Ethnic specific, usually it was severe diseases of high incidence. Usually the screening was sequential, which means, let's say that first the, the mother is going, and then the father of the pregnancy is going. And it was, of course, under the supervision of medical geneticists and informed consent process. But as we are advancing with our knowledge about genomics, we can think about a lot of reasons why we want to expand the test. Let's start looking to them. So first, as we said at the beginning of this presentation, we want to allow campaigns that are compatible with the genomic era, which means we know more about more genes. We want to give more to our patient, to the population, so we are going to be in a better health state. Then there are changing demographies. In many populations, there are inter-communal marriage and there are changed residencies. And as you know, for example, in the United States, there are hundreds of languages sometimes spoken at a very, very precise location, like Queens in New York and so on. Then, what we found was that some founder mutations that were associated in the past, let's say with Finns, you can also find them, albeit in lower frequencies, about other Europeans, let's say. So why not include them? Then we have plethora of mutations, which means that we would like to suggest a robust plex technology. We don't want to start screening one by one with means like RFLPs, TACMAN, and so on. We are looking for major modalities that we allow to screen for thousands of variants simultaneously. And usually, of course, we are mentioning either arrays, microarrays, or next generation sequencing technologies. And then many patients are actually tested during ongoing pregnancy. That mandates a rapid and comprehensive test. So still, and we have data from this, in between 1/3 to 1/2 of the couples are actually becoming familiar with preconception screening during the first trimester of the pregnancy, and they are doing it only then. And because the clock is ticking in pregnancy, we would like to have a very, very fast way to receive the samples to the lab and do the testing. And then we are familiar today more and more with sperm and egg donations, which are often being brought to the community from external communities from, of course, many different reasons. So that is the reason for us to want to do it. I should also, of course, mention that many simply don't know or have false reports of origin, and it's a very good way to screen all the people for the same panels, and then you can eliminate this test. And indeed, the present, we are speaking about an ethnic screening. So expanded carrier screening in reproductive medicine points to consider. Expanded screening is not anymore for a single disease. Carrier screening in the age of genomic medicine. Milder phenotypes might be included. Many times there's a recommendation to screen the reproductive partners to get the two samples to the lab in a concurrent way, because the likelihood to find that one of the couple is a carrier is, of course, very high. And this is why we would like to allay attention and know immediately whether the couple are both carriers or not. And then, of course, we still want to have medical geneticists and informed consent for all couples doing it. Importantly, I would like to mention, it just happened last week. So in between the time where we have submitted this presentation for approval, and until today, the American College of Medical Genetics and Genomics have actually issued a new guidelines, which are, of course, fully concordant with what we are saying here. And now, after we went through the understanding of what is preconception screening, I'm going to move into a live example of cystic fibrosis, which we are going to take it and see what are all the definitions of carriers, residual risk, reproductive risk, and so on. So, cystic fibrosis is a complex and multisystemic disorder which is being inherited in an autosomal recessive manner. And it is actually the most common life-limiting autosomal recessive in persons of North European heritage. So that is, of course, giving a lot of motivation to screen for it, especially as it is 1 in 2,500 live births which are being affected with it. And we also know that cystic fibrosis is being caused only because of CF, because of the CFTR gene. So that means that we have a lot of good motivation to be using this. Now, if we need now to define who are the carriers, what are the carriers? So how many individuals in a population are actually carrying a mutation if we know that there is 1 in 2,500 live births of C kids? So the carrier frequency is actually the proportion of individuals in a population who have a single copy of a specific recessive genetic variant. And how are we going to go to these numbers if we know what is the actual frequency of the disease? And let me try showing to you how we are doing this. So if we are going now to take a look at how we are going to do it, let's take again the results of the cystic fibrosis screening, and let's see how are we calculating back. If this is the disease, we know the frequency is 1 to 2,500. How are we doing this? So if we are going to go and know that 1 in 25 is a carrier, the risk that a mother will randomly have a reproductive partner with a father, which is 1 in 25 as well, and it's 1 in 25 times 1 in 25, and then only 1/4 of the kids are going to be affected. So it brings us back to the exact number that we said, 1 in 2,500 live birth cases for cystic fibrosis. Of course, we can use it now to reverse engineer it. So that means that if we know that a given disease is 1 in 2,500, then we also know that it is we can divide by 4 and then take the square root out, and then we will be able to find out what is the frequency of the disease. So let's try to do it ourselves. So let's say that we have now a population with an incidence of CF, which is 1 in 100,000 live births. We are going to take it back. If we are going to take it back, then we are going to see that if we are going to find 25,000, and there we account for random mating, so the square root of 25,000 is 158, and therefore the carrier frequency is 1 to 158. As simple as that. So if you know what is the frequency of a disease in your population, you have to divide it by 4, then take the square root, and then you will have the carrier frequency of this one. Now, what is the residual risk? The residual risk is the amount of risk or danger associated with an action or event remaining after natural or inherent risk have been reduced by risk controls. What does it mean? Let's say that there is a couple that did a screening for cystic fibrosis and they are both negative. Does it mean that there is zero chance for a kid with cystic fibrosis? The answer for this is no. They still have a risk because we have eliminated maybe much of the risk, but not all of it, which depends, for example, on the number of mutations that were screened for, on the accuracy of the method, and on their ethnicity. That we have to understand now that the actual panel which is being used for the preconception screening is critical to understand what is the situation. So we might think about two different types of panels. there might be a pathogenic variant panel, which is a test that analyzes multiple variant and TWAS for preconception-associated mutations. So let's say that we are screening 23 mutations for cystic fibrosis. We are not reading the full gene. We are only going to mutations that we know that are in high frequency. And then, different from this, is a gene panel, which is a test that analyzes multiple genes. So this test will attempt to read the full length of a gene and see whether there are any mutations that can found there. A good example will be whether for the first one is arrays, which means that we are putting on an array a finite number of mutations that should be screened for, and we are going to screen only for these mutations, as compared to preconception screening based on a gene panel, which we are going to try to read all the genes and find all types of mutations. Of course, we might also find mutations or variants that we don't know what is their meaning, often known as variants of unknown clinical significance. So, therefore, it is critical for us to understand what is the detection rate of our test, because the detection rate will affect directly the residual risk. The proportion of individuals with a particular condition who test positive for that condition when measured by a gold standard methodology is the detection rate. So we need to understand how many people, what percentage of the mutations that we want to screen are actually going to be captured by the panel we are using, because that will allow us to understand what is the detection rate of the carriers within a given population. So if we're going to take a look to this, then let's take a look for CFTR, for example. So for many years, for general population, the American College of Medical Genetics recommended 23 mutations. But as you can see, in Caucasians, that the population carrier frequency was 1 in 25, the detection rate was 88%. For Hispanic American, it was 79%. For Asian American, it went all the way down to 49%. So that means that these 23 mutations cannot capture all the variants affecting populations, and it is varying depending on the population. As you can see, indeed, the final results post-testing is going to be different based on the detection rate that this specific panel can allow. And if we're going to go back to cystic fibrosis again, and we are going to take a vivid example, then if we take carrier rate of 1 in 25 and detection rate of 97%, which means that in a given individual from Ashkenazi Jewish origin, if we screen the 23 mutations that we just discussed, we are going to detect 97% of the variants affecting this population. If we are going to put it into the probabilities formula, which is being brought here to you, which is taking into consideration prior probability for a carrier, conditional probability, which is what does it mean if there's a negative result, and eventually if an individual from Ashkenazi Jewish ancestry, where we know that the prior probability is 1 in 25, and we know that the detection rate is 97%, at the end of the test, if he's negative, he or she are negative, then the residual risk is still going to be 1 in 801. So once again, negative result on a residual risk panel is never eliminating the possibility to be a carrier, and therefore never eliminating the possibility of a sick kid. It's of course making it much more likely. And if we are going to take a look to different scenarios, then you see that if we take the same example for Ashkenazi Jews, Caucasian, and Asian, with the a priori carrier frequencies, with the different detection rates which are being suggested by this 23 mutation panel, let's say, then we see that the residual risk differ dramatically. Of course, you can understand that this is why we want to move into more and more mutations being screened, not only 23, but hundreds of mutations of full gene sequencing, because then the detection rate would be much higher and the residual risk would go far below. And that is the story of expanded preconception screening, elevating the detection rate so that per population we can get much lower residual risk. Let's go back to our couple and take a look at them. So we know that a priori, as you already know, 1 in 25 times 1 in 25, 1 in 25 times 1 in 25 times 1 in 4, the a priori risk is 1 in 2,500 kids will be affected. However, post the test, if now the mother was screened and she has 1 to 801, and the father has 1 in 801 because they are both Ashkenazi Jews and they took the test, then now the chance for a C kid is 1 in 801 times 1 in 801 times quarter, which brings us to 1 in roughly 2.5 million, which is of course very, very low, but again, not zero. So, as you know, now we need to do it ourselves. So let's calculate it for a newborn with CF, and the mother is of Ashkenazi Jewish origin and she is not tested. The father is of East Asian ancestry and he is tested. So now we are going to take a look at it. If the mother is of Ashkenazi Jewish ancestry and she was not tested, she is 1 in 25. If the father is of Asian ancestry and he was tested, he is 1 in 203. So that means that now the overall risk is 1 in 25 times 1 in 203 times 1 in 4, which is 1 in 20,000. Now we are going to see another very important thing which might affect if the detection rate. So as you can see, the issue of no calls. So one individual is being screened for a given number of mutations, and theoretically, in a given specific genotyping procedure, one of the mutations can not work simply because of a technical lab issue, which is something we are all familiar with. Naturally, that will affect the overall residual risk because it will affect the detection rate. So again, for this couple of Ashkenazi Jewish origin, 42% are from this mutation, which means that if this mutation is dropping from one test, then of course it affects dramatically the detection rate. So this is why it is important to be aware of the no calls. And naturally, if we go ahead now, this means that we need to know what to do with no cause mutations. And this is why we allow, using the software of Identify, to actually choose variants that will be handled differently if they have failed in the genotyping. So one have an opportunity to identify a must-have variant, which means that if this variant, for any given reason, is failing, the system will block the release of a report until another genotyping cycle has happened and actually a call was received, whether negative or positive. Simultaneously, there's a different way to handle variants which might be failing in other in mutations which are not so important, that one maybe will not want to block a report because their overall effect on the detection rate is very, very low. And with this, I'm going to move you into understanding what is the software of Identify that can accompany the screening of preconception test, expanded preconception test, because naturally it might become very, very complex to try to screen for 400, 500 genes or 1,000 mutations simultaneously in different populations. So actually the platform allows for 4 different modules. The first of them is the access, which allows it to the actually give the way to take medical history from a, a given individual which is being screened and have all the data ready for the later on calculations of the ancestry and so on. The next module is actually the module of analyze, which we know how to integrate to raw data test and actually calculate automatically the carrier state and the residual risk. The next one will be the insight model, which will actually allow us to have all the data reported and being ready for report, and then, of course, to counsel and to release reports to the patients. If any of you are interested to have a full demonstration of this software, we are very happy to show it elsewhere, but the overall value proposition is naturally to reduce the face-to-face interaction with genetic counselors, to be able to screen many more patients in the given time frame. And then we should conclude by asking ourselves, okay, what do we expect we are going to do preconception screening on the population? So as you can see, there's an example. You can all look for it. That was published in the New York Times as an example. So testing of Tay-Sachs among Ashkenazi Jews, and you can see that it is concluding that 30 years later, Tay-Sachs is virtually gone. Its incidence slashed more than 95%. The disease is now so rare that most doctors have never seen a case. So that's the outcome of preconception screening, of successful preconception screening. And then you can also see that there are declared missions of ministries of health like this one, impact of a national genetic carrier screening program for reproductive purposes. And I've copied this last line here. Finally, expanding the existing test into a uniform, wide genetic panels seem to be the next goal. So the vision and the promise of expanded preconception screening is being fulfilled as we speak, and that is going to become yet another critical pillar for the preconception prenatal arsenal of tests we can allow the productive partners to use, like chromosomal microarray analysis, NIPT, and extended preconception screening. And with this, I would like to thank you all for listening. I would be more than happy to receive questions now, or again, if you want to approach me later on, then that would be, of course, a pleasure to answer the questions. So thank you, and please have a question if you want to.
Thank you, Dr. Bear, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have any question you would like to ask, please just do so. Click on the Ask a Question box located on the far left of your screen, and we will answer as many of your questions as we have time for. Other disease do you foresee disappearing or becoming very rare thanks to this expanded carrier screening approach?
So I think that the first diseases that we would like to have really good grasp of are those that are, of course, making most of the contribution to the sick kids. And that would be, of course, cystic fibrosis in Western populations, and then globally, Duchenne muscular dystrophy, thalassemia, Fragile X, so all the ones that are there. And then, of course, the ones that we are going to see disappearing are the ones that really have an affiliation to a given community. So exactly as I said before, the Finnish heritage disorders about Amish, about populations that we know that there is an access of genetic diseases in them because of a strong founder effect. So that's what I would expect. And naturally, one should always rethink about cystic fibrosis because there are roughly 100,000 kids suffering from cystic fibrosis worldwide. And basically, with the current level of preconception testing that we can offer, we can eliminate almost all cases. So that would be what I would envision that will happen next.
Thank you. Another question is, you mentioned potential analysis of hundreds of genes and thousands of variants. Is there a way to restrict the list of the variants if you want?
Yes, absolutely. That is actually a key feature of the system because different populations and different regulatory agencies and different insurance companies might point to a different number of mutations or genes that they want to be screened for. So actually, it is possible to limit the number and actually to suggest different offerings to different patients from the same clinic specifically for these purposes. So that is a setup that, of course, should be done first time and then can be repeatedly modified if needed. But usually after a first good setup, then there is no need to do it again. But that the answer is to this absolutely yes.
Another question, and that's somehow related to what you just said. It looks quite simple to implement this solution, but are there challenges still to implement the exponential screening?
So I think that, of course, the challenges of introducing any new method to the lab are, are pretty much the same. People need to be familiar with the number of mutations that they are going to be screened, the number of diseases, which might be a little bit overwhelming at the beginning. But this is exactly why there are very strong both laboratory validation processes and very strong software that is making life much easier. And we have very good experience with laboratories adopting this, seeing that they are really becoming mass production laboratories of just tests. So I would say that after a period of adoption, which will usually be, a few weeks to a couple of months, this is becoming very, very routine, and that should be, of course, the case. Another thing that one must realize, and we saw it a few times, variants that were considered to be pathogenic variants. Once you start doing mass screening, you see that they are simply appearing too much in the population, and then you know that they can't be pathogenic. So this is a little bit of studying doing this, but we have not seen anyone failing in fulfilling it after a few weeks to a couple of months. So I would say that it's a straightforward solution now.
Thank you. Another question is why Asian people have higher prevalence of cystic fibrosis?
Oh, they actually have lower prevalence of cystic fibrosis. We don't know why it's always. Remember, when it is 1 in 24, 1 in 25 in Caucasian, and 1 in 68, let's say in Asian, then that means that Asian actually have less carrier state. What are the reasons for this? We do not know. It might be local drift effect. In most cases, we don't have a good answer. In some diseases, like sickle cell anemia, like thalassemia, we do know that there is a strong benefit for the heterozygote carriers, like from being infected with malaria, and this is why there is excess of these disorders in these populations. But it is true for many population genetics. Let's say forces that are shaping the genetic variation in a given population are that it is simply drift, and drift is a sine qua non with saying luck, chance.
Thank you. Looks like we have time for one more question. It's more a technical question. What kind of input data format is your software using?
That would be arrays or NGS, and the software can handle both platforms and can also allow to integrate more results. Let's give a very trivial example. Usually, both arrays and NGS are not very successful with doing Fragile X, and then usually a third method is needed, and the software will know also how to absorb the results of this software into a one coherent report. So I would, to make it brief, it would be array, NGS, and then some is needed for another given variant. The software can do this as well.
All right, thank you very much, Dr. Behar. Do you have any final comments for our audience? Dr. Behar?
I would be happy to receive more questions, or if more examples are needed and actual experience with the software that makes it very easy, then please feel free to contact me, and I will make sure that this information and questions are being answered. Other than this, I want to thank you all for attending this presentation.